and welcome to HCI 509, Research Methods and Statistical Analysis. In this lecture, Lecture 12, we'll talk about correlation. So let's get started. We'll begin by talking about how we calculate correlations. The most widely used method is Pearson's correlation coefficient. It's also known as Pearson's R, and it's the covariance of two variables divided by the product of their standard deviations. The nice thing about doing it this way is we get a normalized measurement of the covariance so that the result is always between -1 and 1. We'll talk about what those mean in just a second. Covariance is the measure of the joint variability of two random variables. So when we think about joint variability, it's discussing how when one changes, how does the other react? So you can think about it in two dimensions as x and y. First, let's talk about a negative Pearson's R value. So the value of Pearson's R ranges between -1 for a perfect negative correlation and +1 for a perfect positive correlation. So when we have a -1, it suggests a perfect negative linear relationship between the variables. So that means as one increases, the other decreases. This means that we can perfectly predict the increase of one if we know the other, or the decrease of the other if we know the first. So when we have a positive R value, this means that we have a perfect positive linear relationship between the variables. Any increase in the scores of one variable will perfectly predict a specific amount of increase in the scores of the other. When we have an R value of 0, this means there's no relationship at all between the two variables. The increase or decrease of one variable does not predict any changes in the other variable. So if you recall, in previous lectures, we talked about 8 participants completing 2 different tasks, one using standard word processing software and the other using word prediction software. So if we look at this JASP, we can see that the rows refer to participants and the second column refers to the years of computer experience each participant had, and then the scores for a particular task for the standard word processing software and the other using word prediction. So we can run 3 Pearson's correlation tests based on this data set to examine the correlation between computer experience, the number of years, and the task time under the standard word processing software condition, the computer experience, and the one under the predictive software condition. And then we can look at the task times between the standard and those in the predictive software condition. So because we have 3 variables, we can look and make comparisons across all 3, taking one at a time. So in JASP, this is what we would have. And there is a sample so you can play around with this data. This is also in the Blackboard website. So we've got the participant information, and then we have the variables here. So computer experience, standard, and prediction. And you can see here we've got sample correlation coefficients, and there's 3 different choices. Pearson's R works very well with interval data, which is what we have here, because there is a standard measurable difference between each of those 3 variables. Now, Spearman's rho and Kendall's tau, these work with non-parametric tests, and these work better with ordinal values. We'll learn more about them when we talk about non-parametric tests in future lectures. So we would check the Pearson's R for our correlation coefficient, and you can see what the results are over here on the right. So if we're going to look at the data, we can see a couple things. First of all, we have the variables both down the first column and across the top. We can see here that this represents the pairing of each of our variables with every other variable. Notice the diagonal has these dashed lines because it doesn't make much sense to look at the correlation between computer experience and computer experience. It just doesn't provide us any information. Let's take a look at each of these values and see what kind of information they have. So if we look at the standard word processing software and computer experience, we can see that we get a Pearson's R of negative 0.723 and a p-value that's less than 0.05. So we could say both the Pearson's R is fairly strong, because remember it goes between -1 and 1. The p-value is less than 0.05, so it's a significant value, and we can say that there is a relationship between the two. It's also negative, so that means that as the computer experience increases, meaning as the time that somebody's used a computer increases, the amount of time it's necessary to complete the task decreases. And this makes sense if you think about it, because as you get more experience, if you're being timed to do a task, you're going to be faster than somebody who may not have experience and needs to get familiar with the mouse or with how Word or whatever software tool they're using operates. Now we look at the predictive software tool, and you can see here that the relationship between the predictive software tool and computer experience is not as strong. The p-value is 0.243, so that is not within the 0.05 that we would normally test at. And you can see the Pearson's R is minus 0.468. So there's a negative correlation, just as we would expect. However, it's not significant. Now we turn our attention to how the standard software typing tool and the predictive one correlate. We can see here that it's a positive correlation. However, it's not significant because the p-value is far too high for us to consider it as significant. So let's talk a little bit about R squared. Sometimes you see R squared mentioned instead of R because it's a more direct measure of the degree of correlation than R. What R squared means is it's the proportion of the variance shared by the two variables. So this can tell us, for example, if we have two variables, x and y, R squared represents the percentage of variance in x that can be explained by y and vice versa. Let's take height and weight. Normally, if we got a group of people and we measured their height and weight, we would see them to be positively correlated. So there's going to be some variance. We'll find some very tall, thin people. We'll find some short, less thin people. And what this means is the relationship's going to have some variance. So R squared is going to represent the percentage of variance in x that can be explained by y. Here's a question for you. Correlations or relationships between two or more factors are always meaningful. True or false? They're not always meaningful. If you remember a few lectures back, we talked about spurious correlations, and that's where we had people who drowned by falling in a pool in films Nick Cage appeared in. And you can see here the correlation was 0.66, which is quite high. However, it would be very difficult to argue that these two have a meaningful relationship. That's where we go now, is identifying relationships between the variables. We talk about causal relationships. A causes B. This is important to keep in mind because just because there's correlation does not imply causation. For example, it's been shown that on days where there's more ice cream sales, we have more people who drown when they're swimming. It doesn't make sense to blame drownings on ice cream sales because it could be that there's something else responsible for both that we're not considering. Just because they're correlated does not necessarily mean the changes in one cause the changes in another. This is really important because a lot of people in their logic make the mistake that just because two things happen together, there's a cause-effect relationship when there's not. So sometimes there is a causal relationship between the two variables. In other cases, there's something called a hidden variable. So this is also called a confounding or intervening variable, which serves to give the underlying cause of the change. So when could we see these kind of confounding variables in our own research? Sometimes people can be difficult to research. Not only do they react to the stimulus being studied, just as we would expect, but also to the experiment itself. And researchers try to design experiments to control for such factors, but that wasn't always the case. Back around the turn of the century, in 1909, Frederick Taylor designed a bunch of experiments to try to come up with ways that factories could be more productive. So the US started looking at assembly lines for manufacture of vehicles and machinery. And Frederick Taylor was one of the pioneers in looking at how he could measure performance on an assembly line. He was one of many, and this led to things like the Hawthorne effect. You may have heard of it. The Hawthorne works in Cicero, Illinois. I think they made like hosiery and items like this. There were some researchers that conducted a series of experiments from 1924 to 1932. And they were trying to look at how they could make workers more productive, because that was really the focus during that age. And they wanted to look at how they could change the factory environment to make things better for the workers, including more light, less light, making the place more tidy, and moving workstations around. And they thought they were onto something. And then all of a sudden they noticed something. What happened was the increases in productivity dropped almost as soon as the researchers left. This meant that the workers' knowledge of the experiment, not the stimulus that they were hoping for, had fueled the boost. So researchers still call this the Hawthorne effect. Sometimes when we observe people in a research environment, they react to us differently than we would expect. We may think that the stimulus that we're introducing, the treatments, are what's changing their behavior, when actually they're only doing it like they're on a stage. They're doing it when they know they're being researched and observed. This could also be what we talked about before when we talked about systematic bias, but I'm mentioning it here because these are the kinds of things that lead to potential discoveries that are actually not causal as we expect. Another one is the Henry effect. If you remember, John Henry was this very muscular railroad worker back around 150 years ago. This was when man was going up against machine, when they're building the railroads. And he said he could outperform any machine. So he really performed his best and actually beat the machine that was building the railroads through brute force. And he did it so much that he actually died from his effort. And this is important because sometimes we have control groups that try to beat the experimental group as a challenge. And they do this because they know that they're part of the group that is not receiving the treatment. And just like John Henry, they want to prove their capabilities and earn respect. So they may be outperforming the experimental group just to make some kind of statement. And this can be a confounding effect on our experiments. So we want to look at how users interact with e-commerce websites, say Amazon or eBay. So there's a significant correlation between the income of the participant and their performance. More specifically, participants with higher income spend longer finding a specific item and make more errors during the navigation process. This is puzzling, right? Could we say that earning a higher income causes people to spend more time retrieving online items and making more errors? I mean, think about it. What else could cause this type of relationship to be seen? The answer is clearly no. But what else could cause this kind of relationship? The truth might be that people who earn more money tend to be older than those who earn a lower income. And typically, people who are older don't use computers as intensively as people who are younger, especially doing things like online shopping. And consequently, they may spend more time to find items and make more errors. So this means that age is the intervening or confounding variable that's hidden between the two variables examined in the correlation. So age is more important to determining how the person performs than their income. So income and performance are correlated, right? Because we did the experiment and we found this, but there's no causal relationship between them. And this illustrates the danger of claiming causal relationship based on significant correlation. And this, again, is something we have to keep in mind. So really, if we wanted to see how this worked, you could see that age and income might be correlated. And age is also correlated with less experience in online purchases and also lower performance on the tasks that we saw. But you can see here that income and less experience in online purchases is only related through the confounding variable age. It's a very common mistake to conduct pairwise correlation tests on all variables and then say something like variable A has a significant impact on variable B. The number of Nicolas Cage movies has a significant impact on the number of drownings each year. The changes in variable A cause variable B to change. Notice that we're giving some kind of causation to these statements. So this can be what we call a spurious relationship, and we have to be careful about this. To avoid this, keep in mind that empirical studies should be driven by our hypothesis, not by observations in our data. What we want to do is we start with a hypothesis, and we can't just look at the data and then come up with a hypothesis once we see the data. Not only is that unethical, it also leads to some mistakes later on. So data analysis should not define the hypothesis. The hypothesis should be independent before we get our data. So in the e-commerce example, you're not likely to develop a hypothesis that says income has a significant impact on online purchasing performance. It would be very unlikely unless you saw a number of other research studies that hint at this. Typically, you're going to come up with something else where it's going to be age has a significant impact on their performance. So we have to be careful here because this statement doesn't make much sense. It's not one that's intuitive. We want to make sure that our studies are hypothesis driven, so we can't be fooled by these correlation analysis results. It's very tempting to see things or patterns in our data and then say, oh, well, maybe I can say this. But because you didn't start with a hypothesis with that in mind, it could be some flaws in your research design. So if the study doesn't have a clearly defined hypothesis before you begin your empirical study, the hypothesis will be driven by the data analysis. And this means it's more likely that you're going to have false conclusions based on what you observe in the data. So to summarize, correlations are useful to identify significant relationships between two variables. We use Pearson's correlation coefficient as the most commonly used test, especially with interval-based data. These are numbers that we would have when we do the studies that were mentioned. Correlation should not be used to look at causal relationships. It's far more difficult to show a causal relationship in an empirical study. Remember, we are talking about how difficult it is to prove something in the first few lectures, and this builds on that. It's difficult to show a causal relationship unless you've got a very well-designed study. So we want to be careful not to be fooled by erroneous correlations. So we want to make sure our hypotheses are locked down before we begin data collection and analysis. Thank you, and I hope this lecture has been informative. I look forward to seeing you next time.